Video on what is electricity. So what do you need to know about it? What exactly is it? So we're going to be focusing mainly on these words. We're going to look at the word current. We're going to look at the word charge. We're going to look at voltage. And we're going to look at resistance. We're not going to do anything else, but this is essentially the fundamentals of electricity. It doesn't necessarily mean it's easy, but it's the foundational understanding that you need to be able to apply to everything else in the electricity topic. So this is what I'm going to try to focus on in this video. So first of all, what is electricity? Well, basically electricity is all about charge. So question is, what is charge? Well, actually, the thing about that is that most people don't really know much about what charge is. We just know what happens when charge is around. So we know, for example, that you can have a positive charge. We know that you can have a negative charge, and if those two things got near to each other, well, they feel a force towards one another. The closer they are, the stronger the force. The further away they are, the weaker the force. And if you have similar charges, they would repel one another. Okay. We also know that some things don't have charge. Some things have charge, some things don't have charge. Some things have a positive charge, some things have a negative charge. For example, a neutron has no charge, a proton has a positive charge, and an electron has a negative charge. So there are a number of different things, and the things that we're mostly concerned about is the electron. We do want to talk a little bit about the proton, but mainly about the electron when it comes to electricity. So that's what charge is. Well, that's what charge does. That's all we need to know about charge. As I say, why? I suppose when I say what is charge, we don't know why some things have a charge, why some things don't have a charge, why this thing has a positive charge, this thing has a negative charge. We don't really get that, and more importantly, you don't need to know that for your GCSE or for your A-level actually. So let's go on a little bit more at some of these other words. Current. So the textbook definition is the rate of flow of charge. But what that actually means is how much charge is flowing per second, essentially. It's measured in amps, which is the symbol for amps is A. By the way, don't confuse the symbol for the symbols for the units and the symbols themselves. The symbol for current is capital I, but the unit is amp. And sorry, I should have said this for the charge, so we just go back to charge. The symbol for charge is Q, but the unit is coulomb, and the symbol for a coulomb is capital C. Okay, so we're going to use these again in a moment. So it's the rate of flow of charge, so the charge is there. So how much charge is flowing by per second. So you could have so if you have something that carries charge like an electron, if you have lots of them, then you're going to be able to get quite a lot of current without having to move them very quickly. Or you can have just a few of them, but they'd have to be moving really, really quickly to have the same current. So current is equal to, if it's the rate of flow charge, those of you who are quite good at maths would know that would mean that current is equal to the amount of charge that's flowed divided by the amount of time that's taken place in order for that flow to have happened. So put that into a triangle. You've got Q at the top, bit of a messy triangle, but like that. Okay, you should know how to. So that rather than spending a lot of energy trying to remember all these formulae, try to make sense of what the formula is. So to me, that makes sense that it would be Q divided by 2, charge divided by time. And once I've made sense of that, then I can put it into a triangle by look at the right hand side, put it in, and put that one in the gap. Okay, so that's current, the next one is voltage. So voltage, symbol V, and the unit is volt, and the symbol for volt is also capital V. So it's a little bit of a confusing one there. What is voltage? It's the energy per charge. So if you've got a load of electrons, then how much energy do those electrons have? And that would be the voltage. Okay, we will often voltage is talked about as potential differences. A potential difference. There is a subtle difference, but for now we'll say it's pretty much the same. I'm just going to draw a box around that main definition there. The energy per charge. So also called a potential difference. Why is it called a potential difference? Because between point A and point B, the electrons may have a difference in energy, a difference in energy per charge. So up here, if they're, let's say that's negatively charged and that's positively charged, up here they've got a lot of electric potential energy. They would very much like to accelerate towards this one here. Once they've nearly got there, there's not that much potential because they've made most of the journey already. So up here they have a lot of electric potential energy, and down here they don't have so much. So the difference between A and B you could talk about as the difference in potential energy, in the difference in electric potential energy. We then say, and then we just say per charge. So this is the difference in electric potential energy per charge. And the thing to so what does this mean? Well, this means that when we measure voltage, we don't actually measure the energy directly. We measure the energy at two different between two different points, and that's why when you measure voltage, you measure it in parallel. So if this is a light bulb, then I would have a voltmeter in parallel, because what I want to know is what is the change in energy per charge between 2 points. I don't want to know, or I don't know if it's even possible to measure directly what is the energy. We just want to know the change in energy between 2 points. So whereas when you measure current, we just want to, it's actually measuring directly what is how much charge is flowing per second. So we measure that in series. So that's voltage, and that's current and charge. So clearly you would have thought that if I increase the voltage, I'm going to increase the current. In fact, maybe if I double the voltage, I'm going to double the current. If that was so, we would say that voltage is directly proportional to current. So if it's directly proportional, if I double the voltage, I double the current. If I triple the voltage, I triple the current. Or if I halve the voltage, I would halve the current. Okay, that's not always the case, but when it is the case, we would say that that's Ohm's law. So some components, some components such as wires and resistors, follow Ohm's law. So a wire follows Ohm's law, a resistor follows Ohm's law, but not a light bulb, and not a few other things. Basically, these are the only two things that actually follow Ohm's law, and even they don't follow Ohm's law when they get really hot. So if voltage was directly proportional to current, you would get a straight line like that. And let's say that if we plotted voltage in there, current there, yeah, we'd get a straight line if it follows Ohm's law. If we look at the gradient, a straight line from the origin, I should say. If we look at the gradient, that would be the change in voltage divided by the change in current. and that would actually give us the final word we're looking for, which is the resistance. The symbol is R, the unit is ohm. The symbol for ohm is omega, which looks like that. Sort of. It's not a great omega, but yeah. So this would be the case, if it follows Ohm's law, if that we have a resistance that is constant. So a light bulb therefore does not have constant resistance, and neither do these two when they get really, really hot. The resistance actually increases for high temperatures. So Ohm's law, that would only work if it's constant resistance. That being so, even if R is changing, even if the resistance is changing, we can still always work it out at any particular time by doing the voltage divided by the current. So key point about this is that this thing I'm drawing a box around, this is not Ohm's law. Ohm's law is saying that essentially the resistance is constant, and that so therefore the voltage would be proportional to the current. So even for a light bulb, you can still calculate the resistance at any particular time. If you measure the voltage, you measure the current, then you divide the voltage by the current, and that gives you the resistance. That doesn't mean it follows Ohm's law, because that is not Ohm's law. That's just how to calculate the resistance. That's Ohm's law, and this graph represents Ohm's law. So I could go further now and start drawing graphs of light bulbs and thermistors and diodes, but that's not what this video is all about. If you want to know more about that, let me know. Feel free to that's maths. Feel free to contact me about any more videos. Okay, thanks, bye.